So in the last lecture, we talked about black body radiation, heat capacity, and we introduced some of the basic concepts of quantum uh, theory and how quantum theory can explain certain phenomena better than when we consider the system to be continuous. So as such, it laid basis to today's lecture, which we will begin with looking at um, typical atomic spectra and state transitions on a molecular and atomic levels. So we've had a lot of theories and calculations that led us to believe that um, a quantum nature of our reality is can better explain some of the peculiarities that we observed. So, and one of the most compelling direct evidence of such quantized nature comes from spectroscopy. So spectroscopy, it includes everything from detection to analysis of radiation, electromagnetic radiation, absorption, scattering, or emission. Um, and it allows us to record the intensity of light intensity transmitted or scattered by a molecule or by an atom, and it is a function of wavelength um, or frequency, reciprocity there, or wave number. Um, so this function is cumulatively called the spectrum, which comes from the Latin word that means appearance. Here is a standard atomic spectra of excited iron atom, and it consists of a series of radiations of very discrete wavelengths. So, and these are very, very narrow in bandwidth also. By that, what I mean is that the distribution of each of these lines is extremely narrow. Now, this is an atomic spectrum. In conjunction with atomic spectra, we can also record molecular spectra. And the molecular spectra, basically, in this aspect, we're looking at the correlation of two atoms within a molecule. They have a freedom to vibrate with respect to each other. They have a freedom to bend. So basically, this correlates to rotational vibrational frequencies. So, and these are also very definite frequencies. So, for example, here we have, let's say, if we look at a peak on one of these, this is these are rotational transitions, and these are vibrational transitions. So, what does that mean? We have two atoms that can rotate around each other, or yeah, they can vibrate. Basically, by vibrate, I mean they can, elongate their distance and then go back and forth. So rotational vibrational transitions, and these are usually low in energy as compared to others, but they don't have to be. By simply looking at these two spectra, it is obvious to notice that the emission and absorption of these spectra are basically a collection of or a series of discrete frequencies. This observation can be rationalized if we can correlate the energy of atoms or molecules also being confined to a discrete volume, which means basically an energy can be emitted or absorbed only in these discrete amounts. Now let's look at what's happening here. Now let's assume that we have three different energy levels here, E1, E2, and E3. Here E3 is the highest energy level, okay? And the difference between each of this energy, we call it, let's call it delta E, right? Delta E. And we can have transitions from in any of these levels to any other level, or to E1. In this case, let's call this a ground level, okay? So we have to, of course, remember the Bohr's frequencies. And if you remember, Bohr's equation, E equals h mu, right? So we have to be able to satisfy this equation every time we have a transition, okay? So, and it is actually correlates very well experimentally, because we have these very discrete transitions. Therefore, upon decay of an electron, for example, from a higher energy level to a lower energy level, we have emission of electromagnetic radiation, which is basically a function of mu, or our frequency. Okay, and this explains why we observe what we observe. We can see several different wavelengths, and each of these correlate to a given delta E. And if we have a larger transition from E3 to E2, from E3 to E1, we have high frequency electromagnetic radiation being emitted. And if we have a small d between E3 and E2, we have a longer wavelength, and we have less in frequency of the energy released. Now here is a very well applicable problem. Let's solve. It's easy. There is nothing to it. Just simple math. As we remember, here are some constants that will come in handy. We have Planck's constant. We have the speed of light in the vacuum, Avogadro's number, and the relationship between electron volts and joules. So now I'm sure you have seen the yellow streetlights. They are basically sodium lights, and they emit the sodium spectra, which are several lines that predominantly lie in 590 nanometers. Okay, so let's see what the problem here is. The spectroscopic transition responsible for the emission involves electronic energy levels that have a separation given by our Bohr's equation, right? So let's see what the delta E here is. Okay, delta E equals h mu, and we know that mu, and of course the information is given us in wavelengths, so we have to obviously transform it into wavelengths, and we know that mu equals c divided by lambda. Therefore our delta E equals to hc divided by lambda, right? So we can plug in the numbers, and we get this transition to be 3.37 times 10 to the minus 19 joules. Now We can take this number, multiply by this here, and get in electron volts. This corresponds to 2.10 electron volts. And then we can multiply that by Avogadro's number, and we will get that we have here 203 kilojoules per mole. Okay. I mean, you can do this for any transition in any spectroscopic data. And now, for example, let's say the neon that has a emission wavelength of 736 nanometers. Okay, please solve it and send it to me. Okay, as an assignment, I suppose. 736 nanometers for a neon lamp. So throughout this course, we'll be going back and forth between the particle and wave properties of light, of electromagnetic radiation. That's why I wanted to reiterate. So what exactly, well, not exactly, what is particle wave duality? It's basically one experiment shows that the electromagnetic radiation, which classical physics treats as wave, also has particle characteristics. And another experiment shows that electrons, which classical physics treats as particles, display wave-like characteristics. That's all it is in a nutshell. So having that in mind, let's move forward. So as we have already talked about, we have observed that the electromagnetic radiation of frequency mu can possess only energy consisting of whole numbers. So 0, h mu, 2h mu, and so on and so forth. This suggests, and this is a very broad suggestion, that that consists of 0, 1, 2 particles and so on, and with each particle having an h mu energy. Well, obviously, if one particle exists, it's h mu. If it's two particles, it's 2h mu, and so on and so forth. Now, this particular setup, if you will, is these particles of electromagnetic radiation. We call them photons. This observation of discrete spectra from atoms and molecules can be pictured as the atoms or molecules themselves generating a photon of energy h mu. Whenever a particle from an excited state is forced down or decays down to its ground state, and the energy released in a form of photon in this case is proportional to that energy transition between the energy states within the molecule or the atom, and it equals to h mu. And given that h is a constant, the only thing that changes there is the frequency, and frequency is directly correlated, obviously, to energy. So as of now, we still have to understand that a photon is a suggestion. As such, we have no proof for it, but we have some experimental evidence that comes from measurements of the energy of electrons produced by photoelectric effect. And photoelectric effect is basically a phenomenon that is observed when an electron is ejected from a metal when it's exposed to UV, ultraviolet radiation. So those experiments have shown some really interesting characteristics, such as, and some of them may seem counterintuitive, but we look at it from a perspective of photon, it makes perfect sense. So first of all, no electrons are ejected regardless of the intensity of radiation, unless the frequency exceeds a threshold value characterized by a metal. So this is very important because now uh, we're talking about frequencies here. Now we're talking about a different type of energy rather than a intensity of the whole radiation. We're talking about an energy of a particle here. Okay, that's one. Uh, the kinetic energy of the ejected electrons increase linearly with frequency uh, with respect to the incident radiation. But again, they're not a function of intensity of this radiation. And the last but not least, even at low light intensities, electrons are ejected. Um, right when the frequency becomes above a threshold for that particular metal. So here is a photoelectric effects on uh, sodium, potassium, and rubidium. So as you can see here, each of these have a specific frequencies here given in electron volts, obviously. And as we stated in a previous slide, regardless of intensity below this frequency, nothing happens. Nothing happens in the case of sodium, potassium, or rubidium. Okay? So the moment the frequency goes beyond this threshold frequency, in this case, for example, for rubidium, then we start observing the photoelectric effect. Okay? And this photoelectric effect is linear as a function of frequency to the kinetic energy of photoelectrons, okay, which is obviously given in E. So these experimental observations of photoelectric photoelectric effect suggest that this effect depends on a ejection of the electron from a metal when it interacts or collides with a particle of enough energy to eject that electron from the metal. So that's very important. The particle itself has to have enough energy. So if we suppose that this particle is a photon having an energy of h mu, so the conservation of energy then would require for the ejected electron to have kinetic energy of me v squared divided by 2, right? Classical kinetic energy equals mv squared divided by 2, right? So this is just basically the same thing, but mass of an electron and the velocity at which it is ejected. So, but here we have another term here, which is intrinsic to the metal, which is called the work function, and it's uppercase phi. So basically what happens here is if we have a frequency which is not high enough, if it doesn't have the energy h mu enough, and it falls short of the work function here, it does not do much. It does not well, it does something, of course, but it does not eject an electron. Okay, uh, so this is when our let's call this mu1 and mu2, and this is obviously this is going to be much larger, and if it's much larger, then we have our our mv squared divided by 2, which is our kinetic energy, which is a function of h mu minus phi. So this very elegantly shows what's happening there, and this is an interesting way to look at it, because we can do some very interesting calculations, such as uh, how many photons do we can we get from some let's say uh, a light bulb of 100 watts operating at a certain wavelength. We might do an example or two on that. So now let's quickly summarize this. Basically, what the previous slide showed is that photoejection cannot occur if our energy of our particle is less than that of the work function for the material, of course, because h mu is simply insufficient to ionize or to remove that one electron from the material. Secondly, the photoelectric effect, which is basically summarized in this equation, predicts that the kinetic energy of an ejected electron should increase linearly with frequency. Okay, not the intensity, the frequency. And when a photon collides with the electron, it gives off all of its energy. So the expectations there is to the electron should be ionized, or rather ejected, as immediately as the collision occurs. Given that the electron is of a threshold energy. Obviously, if it's less than that, it will not be able to satisfy the requirements here to observe the photoelectric effect. So here is a fun example which calls for calculating the number of photons emitted by a 100-watt yellow light bulb in 1 second. And the light emitted is at 560 nanometers, assuming 100% efficiency. Obviously, there is no such thing as 100% efficiency, but to make things easy in this particular case, let's assume it's 100% efficiency. So, just to remember, again, the energy is h mu, right? The total number of photons needed to produce an energy E, right? Therefore, would be E divided by h mu. That's the total number of photons. So, well, we need to first of all, of course, we're given we have our light given in wavelengths, so we need to again remember that mu is c over lambda, right? And we also need to remember that our emitted light is given in 100 watts, right? And 100 watt is power, right? So our energy is basically power per time, right? So E equals power times delta T. So having all of this number of photons, therefore, equals to energy divided by h mu, which equals to energy now here is P delta T divided by h c divided by lambda, which obviously equals to lambda P delta T divided by h c. So without going into details, we have we have our lambda, which is here, and of course we have our power, which is here. Delta t is 1.0. Anyways, if we plug everything in, and the hc obviously it's a constant, n therefore equals 2.8 times 10 to the 20th. And if you put together all this all the values, they cancel each other out because this is just the number of photons. It is actually true that the belief in particle characteristics of light was actually the initial theory, but then it was discarded. But in mid 1920s, an interesting experiment was conducted by Davison Germer, in which they basically performed a diffraction experiment. They diffracted light from a crystal, or electron, sorry, diffracted electron from the crystal. And diffraction is basically interference caused by an object on a path of the wave. Okay. So this such diffraction or such interference results in constructive or destructive interference. And what these are, basically, we have areas where the crest of two waves coincide in time and space, which results in increase in amplitude of the wave, and in other areas in which the crest and the trough coincide, and that results in annulment of the signal. So that's diffraction. So basically, as you might imagine, I mean, we've been talking about the wave and particle dualities. When examining things under an atomic scale, on an atomic scale, the classical understanding of particle and wave, they basically come together. Particles take characteristics of the wave, and the waves take characteristics of a particle. So there was a need to coordinate these events, and we had French physicist Louis de Broglie, who came up basically with an idea that, well, actually he suggested that any particle, not only photons, that travel with a linear momentum PV should have some sense of wavelength, some sort of wavelength being given off. Okay, so let's say we have a particle that travels at mv, right? That's our momentum, linear momentum. Okay, so the de Broglie's relationship here is that lambda has this de Broglie relationship with wavelength, which means a particle with high linear momentum, large p-value, has short wavelength, right? At the same time, this explains very interesting another phenomenon, that in a macroscopic world, in macroscopic bodies, have such high momentum, even when we're moving slowly, that their wavelengths are undetectably small. I mean, for macro world, P is extremely huge, so therefore the wavelength that is radiated by a macro system is negligible. So we will conclude with this today. I'm sorry again if my voice is not perfect. I'm a little under the weather. So basically, let me conclude by saying that Um, Let me finish by saying that all of these experimental evidence and uh, mathematical calculations and theories, we must conclude that uh, any electromagnetic radiation has both properties of wave and a particle. Depends on how you look at it, under which conditions. Um, so this joint particle and wave character of matter and radiation is altogether called the wave-particle duality. Thank you.